Hey everybody, this is Mr. Noyce studying the next unit in honors physics. This unit is called Dynamics. We just finished a long 4-test unit called kinematics. The difference between these is dynamics deals with forces that affect motion. Okay, so it deals with forces that affect motion, whereas kinematics deals with motion without a discussion about the forces that influence it. So what we're going to do now is start this big topic. Now, the father of dynamics is Isaac Newton, and he described 3 laws of motion, and they're the basis of what we call dynamics. Laws of motion. Okay, so let's start with 3 laws of motion. Isaac Newton, he lived about 1700s. Okay, he also wrote the law of gravitation, which we'll talk about in another unit. So let's start with the first law of motion. You should know these. So you probably heard this before. An object at rest remains at rest, and an object in motion remains in motion with constant velocity. That means constant speed in a straight line. Okay, so constant speed in a straight line. So an object at rest will remain at rest. An object in motion will remain in motion with constant velocity, meaning constant speed in a single direction in a straight line. Unless acted upon by a net external force. Okay, when we say net external force, we're talking about, you might have called it an unbalanced force, a force that is not balanced out by other forces. So that's what we mean by a net external force. And the symbol for a net external force is this, F net, or sigma F. Okay, if you have a net force on an object, it will not be moving, it will not be at rest, and it will not be moving at constant velocity. Okay, that's a very important concept. If you have a net force on an object, it will not be moving at constant velocity if it's moving, or remaining at rest if it was at rest. Okay, so that's Newton's first law of motion. Examples. If you're sitting in your car, and your car suddenly stops, you will be you'll be pushed forward, depending. You'll be pushed forward. Well, you'll not be pushed forward, but that's a bad picture, sorry. Your upper body will be pushed forward, right? If it stops, if the car stops. Okay, if this was really exaggerated, you weren't wearing your seatbelt, and the car suddenly stopped, you're an object that was in motion, and you continue moving with the speed of the car forward. If the car suddenly stopped. When you were like this, you were part of the car, moving with the speed of the car. Car suddenly brakes, your body lurches forward because it continues to move forward. That's the reason seatbelts are so important. Also, headrest. If you're in the car, jeez, and the car suddenly hit from behind, if you don't have a headrest, or it's not adjusted right, your neck can be broken because your head is an object at rest, and if the car suddenly lurches forward, your head, which is not connected to a seat, because the headrest is too low, your head will remain at rest while the rest of your body, which has a net force on it, will move with the car. You might break your neck or get severe neck injury if that happens. Okay, it's just an example of the first law of motion as applied to riding in a car. Now, this first law is called the law of inertia. And by definition, inertia is the tendency of an object to resist a change in its state of motion, either its motion or its state of rest. Okay. So, if you want, inertia is similar to the word we have for mass. Mass is it's kind of hard to define it. It has to do with the heaviness of your atoms, but that's not a good term either. So that's not a good definition either. So inertia and mass. A mass being the quantity of matter. Can I go in there? The quantity of matter. Okay, so if you have a lot of mass, like this fat cat, it's going to be hard to push you around if you're moving. If that fat cat was running and I tried to stop him, it would be difficult to stop him. The bigger your inertia, the harder it is to get you moving or to stop you if you're moving. So let's leave it at that. Let's look at some question. In the absence of a net force, sigma F, sigma, I write those sloppy, sigma looks like that. In the absence of a net force, a moving object Well, this is the first law. It will stop immediately. No, it'll keep on moving. Slow down and eventually come to a stop. No. If there is friction and net force, it will come to a stop or drag. But that's a net force. It'll go faster and faster. No. You need a force, external force to make it move faster. It will move at constant velocity. That means constant speed in one direction. That's the first law of motion. When the rockets of a spacecraft are suddenly turned off, well, it's already traveling in empty space. The spacecraft will, well, you took away the force that was causing it to accelerate, but it's not going to stop immediately. In fact, it will not even slowly slow down unless there's drag or friction. And we're assuming there isn't in empty space. There's no friction. It's like a vacuum. Go faster and faster. Well, that's just not imaginable. I mean, you turn off the rocket engines, why would it go faster unless there was another force attracting it? Move with constant velocity. So there we go. Another definition, an example of the first law of motion. You're standing in a moving bus facing forward and you suddenly fall forward. Okay, so let's say you're standing there. Then suddenly you fall forward. Well, you're an object in motion with the bus. But how would you suddenly move forward? Because the bus stops suddenly and you're going to fall forward because you're an object in motion. And the force that's holding your feet to the ground isn't enough to keep you glued to the bus floor. So your body's going to continue moving with constant speed forward. So you can assume that the bus suddenly stopped. Okay, if the bus suddenly accelerated, you'd be pressed against your seat, right? You guys who race around in your cars, when you push on the gas, you're pushed. You feel like the seats, you're pushed against the seat. That's not true. The car's moving forward. You're moving at the same velocity that you were before, and the car accelerates forward, pressing causing the force you feel of the seat pushing against you. That's another example. Okay, so let's go next page. Newton's second law of motion. Well, Newton's second law of motion takes up where the first law ended. So we already know this. Before I talk about the second law, let's just point out a few things we know. In order to accelerate, you need a net force on you to accelerate you. In this case, I guess these guys in this luge, this sled, have to be pushed at first to get them to move. Okay, they have to have this guy right here, this team right here pushing them in order to, well, you can see this guy right here, I guess, here. This is kind of wasting time. This guy right here looks like he's pushing. And then he'll hop in, probably. Yeah, he'll push it and then hop in, I guess. I don't know what. But in order to get the sled moving, accelerate it, you need to have a net force, an outside force, the guy pushing it. So how does the object respond when a force is applied? It accelerates. Now, we already talked about this. Acceleration could be slowing down or speeding up. It could be slowing down or speeding up, depending on the direction of the force. So in this case, the sled is moving, is with a net force like that, the sled will accelerate in that direction to the left, and the speed will increase as increases. If the sled was moving that way and you applied a force right there, a net force right there, the speed would decrease. Okay, so if the force is opposite the direction of the motion of the vehicle, it's going to slow down. If the force is in the same direction as the motion of the vehicle, then the V will increase. We learned that before. The second law states that in order to accelerate, an object has to have a net force on it. Now, we can put that in equation form. Net force equals the mass of the object times the acceleration given to it by the net force. This is the second law in math terms. Okay? So you should already know that the acceleration is a vector. A vector needs direction in order to define it. And the net force is a direction, is a vector with a direction. And the net force and the acceleration are vectors always with the same direction. Okay, so the direction of net force is the same as the direction of the acceleration given to the object. Now, that net force could slow down or speed up the object, like I just said before. Okay, so the units for mass is not weight. The units for mass is kilograms. The unit for acceleration is meter per second squared. And then if you multiply those two units together, you get kilogram meters per second squared. But that is what we call a Newton. A Newton is a unit of force. Okay? So, the mass has to be in kilograms, the acceleration, of course, meter per second squared, and the net force has to be in newtons. Okay, by the way, a newton is about 2.2 pounds. We don't use pounds in physics or science because we use the metric system. But, so a newton's about, whoa, that's wrong. A newton's about a quarter pound. 2.2 newtons is a pound. So it's approximately 1/4 pound. That was a mistake. Okay, so if you want a quarter pounder at McDonald's, you'll get a Newton burger. Okay, so 3.5 kilogram object. Okay, that's mass, kilograms. Acceleration of 5 meters per second squared, 0.5. That's accelerated. What net force does the object experience? Well, according to Newton's second law, net force equals ma. So that equals 3.5 times 0.5. Okay, so that would be 3.5 divided by 2, 1.75. So that would be that one. Newtons. Okay, these are easy. So here's the net force. Here's the mass. How much does it accelerate? What's the magnitude of its acceleration? So net force is equal to ma. So A equals net force divided by m. Net force is 12 divided by 36. It's like 1/3 meters per second squared. Okay, so these are all very basic. You guys can look up this if you want to. Let's do this one quickly. Okay, meters per second squared, acceleration, net force, newtons. What is the runner's mass? So F net equals ma. Oh, we're looking for mass. So mass equals net force divided by A. So it equals 189 divided by 3. 1, 2, 3, 4, 5, 6, 7. About 70, right? No, about 60 something. So I'm assuming at that. Kilograms. Oh, these are good questions. A net force accelerates a mass with acceleration. Okay, same net force applied to mass 2m, then acceleration will be what? Okay, so here's how I do. These I call what if questions. And I'm going to ask you these pretty frequently. Okay, so net force stays the same. So what if I double the mass? What will happen to the acceleration? Okay, I did not change this. I did not change the same net force. Net force is the same. So all you do is 1, this, is equal to 2 times what? And that's your answer. So question mark equals 1/2, which is equal to whatever the acceleration was before. It's now half of it. So it'd be that answer. Okay? So these are what I call what if questions. If something stays constant and change one of the other terms, what does that do to the remaining term? And I just make a little math thing out of it. Okay, constant net force acts on an object. The object will have a constant. F net equals ma. It'll have a constant acceleration. That means the speed will either be increasing or decreasing. So it can't be that. It can't be constant speed. It can't be constant velocity. And why would acceleration increase unless the force increased? Net force. Okay. Okay, so here, this is all repetitive. Now, sometimes you'll see an arrow over this to represent that it's a vector, net force. All forces have directions. They are vectors. And we know how to add vectors easily. What is net force on an object? So I think I'll work this. This is very elementary. We're going to expand on this. So, free body diagram, FBD. It shows the forces acting on an object by arrows. So, a 5 kilogram would be acted on by a 20 Newton force to the right. Okay, here's F1, 20 newtons, and a 30 Newton force also to the right. So I'm going to put a 30 Newton force like that, F2. So what is the net force? Well, they're pointing in the same direction. And so basically, this is 20 newtons. This is 30. Notice how I made the 30 a little bit longer. You should do that when you're drawing free body diagrams. Net force is, because they're going the same direction, you just add them. Then you say to the right, because you got to specify the direction. So if the vectors are collinear and they're pointing the same direction, you add them. If they're pointing opposite directions, you subtract them. If they're at right angles, you do Pythagorean theorem. We'll do that one later. Okay, so they answered this. They drew them differently, but that's okay. They're still pointing the same direction. Heads to tail, right? If you want to do that way. So 20 plus 30 is net force equals 50 to the right. Now, if I said what's the magnitude of the net force, you just say 50 newtons. Okay, so they did all that. Wow. Okay, so two forces act on an object. One force is 40 newtons to the west. Okay, west is that way. The other force is 40 newtons east. Okay, what is the... I guess it didn't show up. What is the net force acting on this object? Okay, so, well, heads to tail if you want. Or you can say 40 plus a negative 40. Okay, if I heads to tail these vectors because I'm adding them, because they're going opposite ways, I'm really subtracting them. 40 minus 40 is 0, or start to the finish would be 0. Just like we did at the beginning of the year. So net force would be 0. So it would be 40 minus 40 equals 0. One force is 8 north, other 6 south. Okay, here's the object. Let's make up north. 8 newtons north and 6 newtons south. Notice how I'm drawing it slightly smaller. So make north positive, south negative. So the net force is equal to 8 plus a negative 6 is equal to 2 newtons. You could do the head to tail method if you want. 8 here, then 6 here, and then from the start to the finish, we get 2 newtons pointing up. Now, I'm not going to say up, I'm going to say north. Okay, remember you got to go from the start to the finish. That direction. Okay. Okay, now they're being a little tricky. Not really. We got a force of 350 pointing upwards. We got, that's F1. Then we got a force of 450 pointing down. What is the acceleration? The acceleration of the object. So F net equals, whenever you see acceleration on these problems, you just use the second law of motion. And that will show you that. Okay, what is the net force? Well, negative 450, because plus 350. Or you could do plus 350 minus 450. Okay, and then the mass is 20 kilograms. Okay, so negative 100 equals 20A. So A is -5 meters per second squared. Okay, so very simple, very straightforward. Except we had to find net force, and then we use the second law. Okay, now, before I go on, let's go back to the second law. Some concepts. So I'm going to go back to this equation. Now, the way Newton expresses was that for a given net force, mass and acceleration are what proportional? Inversely or directly? So, just think about it. If I kicked with a certain force, or I pushed with a certain force a bowling ball, and I pushed with the same exact force for a given net force, I pushed a tennis ball. Okay? Which one, well, I'm pushing it, which one would accelerate and come off my hand with a bigger speed? Well, of course, the lower mass one. So, the smaller the mass, for a given force, for a given net force, the smaller the mass, the bigger the acceleration, the bigger the speed it comes off my hands, therefore the bigger the acceleration. So these are what proportional? Inversely proportional. Okay? We could also do this. For a given mass, we could say a second one like this. For a given mass, so let's do a bowling ball. And a bowling ball, same bowling ball. Okay, for a given mass, along with the bigger force, we'll have the what acceleration. Okay, so the ball on the left, the bowling ball on the left, I apply bigger force. The bowling ball on the right, I apply a smaller force. So for a given mass, the greater the net force on that object, the what the acceleration. Okay, what the acceleration. So if I increase the force on a ball, I kick a ball harder, of course it's going to accelerate faster at a greater rate, and it will come off my foot or my hand faster than if I applied a smaller force. The greater the net force, the greater the acceleration. So I can say for a given mass, the net force and the acceleration are what proportional? Well, greater the force, the greater the acceleration. As one goes up, the other goes up. They are directly proportional. Now, you don't memorize this, you just think it out. You can memorize it, but just think it out. And then final case. What haven't we held constant yet? Okay, we held the mass constant there. We held net force there. And so how about this? For a given acceleration, F net and mass are, proportional. So think of an example. So let's say you have a car. Guy's driving the car. And right next to the car is a guy on a bike. Okay, they're at a stop sign. Okay, or they're at a stoplight. The light turns green. Both the car and the bike, at least at first, are nose to nose for a while. They're accelerating at the same rate. So if these have the same acceleration, they go from 0 to 10 meters per second in the same amount of time. Same acceleration. They pick up speed at the same rate, at least at the beginning. Which one's so same acceleration. Of course, the mass of the car is much greater than the mass of the bike, but they have the same acceleration. So who is applying the greater force on the net force? The engine on the car or the bike? The guy's pedaling, the guy's force on the pedals. Well, obviously, the engine of the car is applying more force. I hope you know that. So the bigger mass takes more F net to accelerate at the same rate than a smaller mass. So we can say the bigger mass, more. So we can say these are directly proportional. What? The net force and the mass for a given acceleration are directly proportional. So you should know that those concepts. Okay. See, I'm at 36 minutes, so this is a good ending point.